Okay, so this is a summary discussion of what the Excel functions are that you need for hypothesis testing. It really brings us all the way through pretty much 4/5 of the class right now. When we started out, we understood that we had such things as normal distribution out in things that we measure. Okay, so it looks like this. It's symmetric. The mean is in the middle for perfect data when we have an ideal data set. Okay, so if we're talking population, we'll have a mu. If we're talking about a sample, we'll talk about x bar like that. Okay, and we know when we calculate the standard deviation that one standard deviation, once we calculate it and we score it on the x-axis, ends up on the shoulder. If we measure another standard deviation, it measured out into the middle, and a third ends up near the tail here. Okay, and so this is what we call the empirical model. Is we're just interested as a baseline for all people speaking about statistics and normal distribution. We use this. Okay, so we use the empirical model. Okay, and what we've learned is that 68% of the curve lies between -1 and 1 standard deviation, okay? And about 95% lies between plus and -2 standard deviations. And then about 99.7 lies between plus and -3. Okay, so how did we learn that? That's a little bit of what I'll discuss here, but that's the empirical model. Keep that in mind and memorize it basically. The 68, 95, and 99.7 marks. Okay, so that means that you're able to understand what the normal distribution is about. We understand that the total probability underneath the entire curve is 1. Okay, and how we got around to the 68 is what we did is we subtracted from 1 the area up to this point, and then we subtracted it again because of symmetry, because everything above the point on the other side of the mean, okay, those two are equal, so we subtract 2 of those. Each of those was about 16%. Add those together is about 32%. Subtract from 1 and you get 68%. So that's the principle there. Okay. Now, what is the z? What is the z all about? How do we do that? It's so that anybody in their native units here, so these are native, whatever you're studying, okay, we can convert to a standard model. All right. So we've learned how to translate that. How do we translate the native units over? What we do is where it ends up is that we end up with a z distribution that looks the same, okay? But what we've done is we've shifted it or translated it, and we've scaled it, okay? We've scaled it so that the mean ends up in the world of z as 0, okay? And for z is measured by your point of interest, how far it is from the mean, okay? Because that could be mu, okay? It's either x bar or mu. How far away is it from the mean? How many standard deviations? When we divide by the standard deviation, we're actually just naming how many standard deviations, and it's typical for a table or for any kind of learning use. We don't push the envelope here, but most interesting things happen between 0 and plus and minus 3 or 4. Okay, so for most discussion, we'll talk about plus and minus 1, plus and minus 2, plus and minus 3, and sometimes we'll go out to plus and minus 4. Now when we talk about 6 sigma. Okay, we talk about 6 sigma, that goes out even further to plus and minus 6. Okay, that's why they call it 6 sigma, but we're not going to learn about that in this course. Okay, all right, that's all we did was we've translated anybody that's studying biology and they have some kind of bugs per square millimeter in a petri dish to us studying in business the social sciences, because business is actually considered a social science here, how people react, how they behave, what causes them to react. Okay. All right. So that's what the z is all about, and that's how we calculate it. So the first number, I want to create an arbitrary example here. In the first case, I'll write it in a little bit different color here. In the first case, what we'll do is we're going to show how to calculate the z. So normally you can go to the table. Okay, you can go onto the Google or Google out a z table out there, and then all the tables are arranged either from sometimes -4, sometimes -3 to 0, or some tables will show the other way. It'll show 0 at the top and maybe positive. It'll go to 3, something like that. All right, so you'll see different variations. You have to see what the edge coordinates are. This is going to be the z going in. Okay, so this is how many standard deviations the point of interest was from your mean, essentially. Okay, and what's the table filled with? It's filled with probabilities. Okay, so it's going to range from, if it's very, very small here, the probability would be 0, as an example, like 0, 0, 1 here. And as you get up to the point where z is equal to 0, okay, so that would be half of your graph. You're looking at area of half the graph up to the mean. So when you get to 0, it's going to be 0.5. Okay, so that's what you see. You should check and understand what table you're looking at. If you look at a positive one, you'll start at 0.5. This is where z is positive, and it will go all the way up from probability 0. From 0.5. Let me do that again. From 0.5. All right, and it's two-dimensional. It'll go all the way up to just about 1. It will never hit 1 because it's asymptotic, but it will be like 0.9999, probably another 9 in there, somewhere in this range. Okay, that's how many 9s there are in the table and how many zeros you would have on the other table. Okay, so that's what we're going to use Excel for. All right, so I'm just going to pick something here. Okay, so I'm going to imagine some data. Let's talk about the temperature here. Is on the 19th of April. So the 19th of April, 2020. Okay, I'm looking at a thermometer literally right now, and it says 61. I'm going to say that's probably pretty average. Let's call, I'm just making this up. Let's say the mean for the last 100 years of 19th of April, the average high temperature was 59. I'm going to hedge a little bit. I'm going to say that it was 59. Okay, so if you're making up this data, what kind of variability do you think there is in the data? Okay, so one thing is, you think about temperature at all, we could probably be as low as 30 degrees. I would have to suspect we could hit a 29 degree on this, and I would suspect that we could hit a 79. So I'm almost guessing from a minus 30 to a plus 20 is a sort of range. This is just using common sense here, okay? But likely it's going to be within the range of 59 by what? Just probably within 5 degrees. On average, it's going to be within 5 degrees. Well, guess what? That's what we talk about the ADMAP, okay? That's the average distance to the mean of all the points. By feel, we'll say, yeah, it's probably about 5 plus or minus 5 degrees around 59. That's what we're talking about ADMAP, okay? But of course, when we get to math, we have to be, we have to consider that it's actually the standard deviation, okay? Which we figured out. The standard deviation is a little bit of a contrived version of the ADMAP, and it will always be bigger than the ADMAP. Okay, so the standard deviation here is, we're going to take a wild guess, and we're going to call it 5. No, I'm going to call it 6.0. Okay, just keep it round. 6.0. That's supposed to be a 6. Okay, so we're going to say the standard deviation is 6, like that. Okay, why? That's because we want to find the probability that the temperature, let's see, what's the probability the temperature will be less than? Let's subtract the standard deviation, and we're going to come up with 53. Okay, what's the probability the temperature won't go over 53 next year? Okay, so if we can depend on our data, that's when we use all that we've talked about so far, and we end up using the equation to get to z. Okay, so now we have everything. We've guessed at what all these numbers are. We gave some ideas about these numbers. So if we calculate the z, okay, we could do that. We'll just run it out. We'll just say is equal to, the point of interest is 53 degrees. Where, how far away are we from the mean? Okay, and we're going to divide by the standard deviation we guessed at was 6. Okay, so that's our z. Just as we said, I kind of picked the numbers right. So we're exactly 1 standard deviation down. Okay, so I arbitrarily picked 53 degrees here, which happens to be exactly 1 standard deviation down. So that should demonstrate a little bit about what we're doing here. Okay, so now the trick is, what's the probability? We have the z. How do we get the probability? Well, we either could go to the table over here, like that, or what do? We can run norm.dist. Okay, and as soon as I put in that, it's going to give me the same. We're going to punch in the same numbers here. We're going to type in, he wants to know the point of interest was 53 degrees. Okay, standard deviation was 6. Well, I've missed the mean. It's 59 is the mean, and 6 is standard deviation, and then we do true, so we get a cumulative form of the version of the formula here, and we get 0.158. Well, that's almost 16. All right, that goes back to my original discussion here. We just happen to pick a problem where we're using plus and minus 1, and that's where we get the 68 from, because if we take that equals 2 times this, okay, so that's an area. So that's the area. That's the area under the curve up to 1 standard deviation. So the probability is, in our case, the probability is about 16% of the days will end up being cooler than 53 degrees. Okay, so that's the first formula that we use. Okay, so if we continue to move here, to illustrate the next couple of equations, what I'm going to do is drop in problem 7.7 here. Okay, and what we have here is a problem where students, I think it's college students, doesn't say what students, there's a restaurant that has across the nation some offering on the menu that ranges from $5 to $17.34, $5 to $17.34, and they know the standard deviation is $2.14. There's 28 students. They state that the average price is 5.75. The students of the sample of these 28 students, the students have also stated that they are willing to pay more than $6.50. Okay, so your restaurant chain, how likely is it that these students are not going to use your restaurant? Formulate and conduct a hypothesis test to determine if you can conclude that the population mean is less than 650. Use a level of significance of alpha equal to 5. Okay, so this is something that's probably a real world problem. We're looking at seeing a restaurant chain. Are students going to come and eat here? Okay, so what I'm going to do is I'm going to drop these numbers into a table here. Okay, so there I've dropped in the key numbers. The sample average was 575. The population sigma was $2.14. Remember, that's your variability as standard deviation is in the same units as your native units of what you're measuring here, and is equal to 28. The alpha is 0.05. We want to know at a confidence level of 95%, okay, or the level of significance is 5%, and mu, so a population mean, is thought to be 650. So we might be a competitor of this chain. So that's why we maybe not be able to go to the original chain and get the information directly from them. We're doing a sample. We want to figure out whether we can beat the price or value for students for a certain restaurant. That's one way to take a look at this. Okay, so the first thing that we are going to calculate is we want to know the number to beat. What do we know? Let's draw it out. Okay, let's draw it out first. Okay, so get things in perspective. Always draw what you have here. We have a suspected mean of 650. Okay, the null hypothesis I kind of hit up there was that the price in the restaurants is greater than or equal to 650, and the alternate is less than 650. Okay, so it's either H1 or HA. Okay, so it's less than 650. So we have a left-hand test here. We have to figure out at alpha is equal to 0.05. We have to figure out the Z crit. Okay, this is the number to beat. And then we're going to calculate our actual test statistic. Using the Z statistic, we're going to figure out whether we beat that or not. Okay, so think about it. The test statistic has to end up to the left. Okay, so we're going to look at this problem two different ways. One with the region of rejection over here, with the Z crit versus the actual test statistic from the sample data, and we can reject it that way. And then we're going to change the parlance of this. Then we're going to take a look if the p-value, it's the same thing. It's just a numeric conversion. It's nothing that changes any equation here. We're just going into, say, a different reference system. So it's the p-value if it's less than alpha. So this is alpha right now. So we took alpha and we calculated the Z crit from it. Okay, that's a terrible alpha in there, so I'm going to get rid of it. Okay, so alpha is the area down here. That's 0.05, 5% of the curve down here. And we just got Z crit from that, okay? So the same thing, we have to do the test statistics. Let's figure out what Z crit is, okay? So the first thing we do is Z critical, okay, is what? And this is the other formula that we need to do. We need to do so we need to do an inverse formula here. We need to do a norm dot S dot inverse. And what you feed that is the probability, okay? So we're going to use alpha here. Okay, so this is going to give us the Z that goes with that probability. Okay, so we get minus 1.644, etc. Okay, so I'm going to bring that down a little bit. We'll just use 2 digits. Okay, now we have to do the test statistic. Okay, so the next thing we need to do is just use our test statistic equation for the Z. Okay, so Z of the test statistic is equal to, it's going to be the mean of our test, how far away it is from the population mean, which is going to be 650, and we're given the standard deviation here, so it's going to be the standard deviation over the square root of n. All right, so I'll put that equation in here so it's obvious, and one of the tricks or built-in behaviors, if we take Control C, if I go up and I do a Control C on that, okay, I can reveal what the formula looks like. Okay, normally if I just insert it again here, it's going to put the formula in. But in Excel, if I put in an apostrophe before it, then it just treats it like text. Okay, so that's the formula right there. Okay, so that's how we get the inverse. If we give a probability and do a norm.s.inverse, we get the accompanying or associated Z critical with it, or Z at all with it. Okay, so the second thing is we have to do our test statistic.
Really?
Okay, so I'm going to put this test statistic in here. It's going to be equal to, we need some parens. What was our test average minus what we assume the population average was, divided by the standard deviation, divided by the square root of 28. More parentheses there. There we go. So our test statistic, what was our Z crit, was 1 minus 1.64, and our test statistic is to the left. It's outside. It's in the exclusion area over here. So it's 1.85. So it's looking good so far. All right. So we can already say that we can reject the averages over 650. You can see that we're in the exclusion area here. In other words, the data from our test it punched through the threshold. We went outside the threshold, and this is for the left-hand side. The Z crit is more negative. It's further away from 0. Now, likewise, our p-value, remember what alpha was? Alpha was up to the Z crit. Our p-value is the probability up to the test statistic. Okay? So how are we going to do that? We need to get the p-value. Okay, and all we need to use is the other formula that we're talking about. Okay, and to get that, we use a related formula. It's equal to norm.s.dist. Now remember, norm.dist, you need to put all the parameters in. Here we want to have, give me the test statistic, and I will give you the probability associated with that. So we're going to use that. We have to put in true for cumulative. Right? And I'm going to punch in a couple more decimal places in there. Okay, so the area, our p value, so p, now I can write p in a different color up here. Okay, so our p goes up to not alpha, but to our test statistic, and that area is 0.0318, or the probability. You can think of it probability, but really just think about it. The area is 0.0318, and that's our test of significance. Okay, so our Z of the test statistic must be more negative. Okay, more negative. It's larger, but it's in the negative range, 1.85. Okay, we've already passed the test, and we're just showing that if we use the p-value, which is more common, all right, then we use this norm.s.dist. Okay, that formula, we use that on our test statistic, and it came out that the area is less. So you could see that they're how related they are. Okay, so 0.0318, the area is less than, not equal, is less than the 0.05 of the alpha. And to finish this off, I'm just showing here that equation 2, we used norm.s.inverse of a probability, that was our alpha, to figure out what the z value was. We calculated our test statistic as we normally do. You'll do a lot of that. And then to get the p-value, which is a probability, we took the computed test statistic and put that into the norm.s.dist. Okay, so I just want to make sure all the three equations are clear to you there.